you were comfortable with linear regression and had done quite a bit of it, or nonlinear, excuse me, I would say go ahead and do the second one because it's easier than doing the transformation. In terms of once you transform the data, it becomes hard to like mentally connect the values with the true values. Um, but option one works pretty well for most situations. If you want to try a linear regression, try a transformation of the data to get it to be more linear. Okay, so
P-values more than fail to reject a null.
all right. So that was just basically throw it in there to help you understand that sometimes the relationships are not linear.
Is that it?
Number 9.
Yes. Haha. We're done with that one. That's fine. We're done with 3 out of 18. Gotta be kidding. Oh my. Number 9. Sloppy. Number 9. Month and disc players sold. Wants to understand the growth pattern of the monthly sales of Blu-ray disc players. Oh, 2 years. The managers have recorded the relevant data in the file. Have the sales of this product been growing linearly over these months? So that's going to be the same thing we've been doing every time.
Players 10 months.
Which one is Y? I think it's disc players sold is Y.
Month. Okay, so disc players sold is my Y variable, and X variable is the month. You don't deal with time series too often, other than I mean, there's certain common ones that you see all the time, like the stock market and such. But other times you just
You sniffed, and you sniffed, and you sniffed, and you sniffed. And I could probably fit this on this tab because it's very little stuff here. That's funny. Wow and wow and wow. Stop. And going to be this one. And this one will be this one. And we'll have output range of right here. And please fit on the page. Please. Thank you. So what we have here is a 0.89, 0.80, and a very small p-value, so it looks like it worked. Yippee.
Since we're usually
So what are we answering here? Have they been growing linearly? Explain why or why not. Well, do we just have to, do we look at the same three things that we've been looking at every time, like this, this, and this? And we'll see.
that is variables that we see. And have they grown linearly over time? It appears that the answer to that is yes. Looking at our r and our r squared, our significance.
You sniffed.
So since
Okay, so first of all, more than 70, so strong relationship. So 0.7, so strong relationship. And then this percent of the variability in sales is explained by 80% of variability in that was funny. Sales of disc players is explained by I'm a dum-dum. I don't feel like doing it by the month. Save, and since the p-value is less than alpha, null is rejected. Since the p-value is less than alpha equals 0.05, rejects the null, conclude that there is a significant relationship. There's a significant linear relationship between the disc player sales and the month. There is a significant linear relationship between the something and the something. The disc player sales and the month. Disc player sales and the month. I'll just do this. Merge and text wrap. There we go. So conclude that there's a significant, and that's all. Why would we need to do anything else? There's nothing else to do here. And we got 0.89, 0.80, and 3.06 to the -9. Just making sure. Oh, come on. We have to do that too? Come on, man.
the intercept was 604. So for each additional month,
Player sold equals something, something, something. Why do we have to do this? Players sold equals 604.38 plus 152.92 times the month.
the passive.
For each additional month that passes, there are something more players sold. For each additional month that passes, there are something more disc players sold. there are 153 more disc players sold. Do we really have to do all that stuff every time?
Dealing with simple linear regression, I highly recommend plotting the data out. And so I'm going to highlight the data, go to insert and scatter plot, and get my scatter plot. And the main thing is that this supports that basic trend, right? We add our trend line. And if we bring that in more data,
Do we have to do this?
in our R-squared chart, right?
No, I don't want to do all that. I don't want to do that.
Just move it so you can see it. And what we're seeing here is, yes, there is a significant linear relationship. The dots are pretty close to the line. But what I'm seeing also is that there seemed to be a trend where it went really rapid for a while and slowed down. And if you look at just these last 10 months, it almost is looking flat. So if you're predicting for month 30 to be up here somewhere, that might be inaccurate. You might be right. You might have plateaued out. These might be your max sales limit. So I'm pointing this out because you should always look at the scatter plot of a simple linear regression to see if there is failure, if this is what you don't want to model. Could be a very small, but actually it becomes even less easy to see. The dots are all over the place. But this math that has subjective aspects to it.
I don't know. Should I put the plot at the bottom? I don't want to. I'm just gonna put the. It only takes 2 seconds, so I'll just put it down here. Oh, come on. And also I have to add the trend line. There's the trend line. Save. Good, I'm done. So that's it. We are now done with 4 problems out of 18. We are done with 4 out of 18. Number 16. Oh no. Now we have to go all the way to the next problem set. Oh. Number 16. Number 16. Number 16 is number 16. No, there's 2 parts of it. Oh no. Maintenance expense and number of miles driven. And the, oh no, don't tell me we have to do multiple regression. Oh. Estimate multiple regression equation. Interpret each of the coefficients. Why is the magnitude of miles driven coefficient lower than the magnitude of age driven? It's because it's not as important in predicting maintenance expense. Interpret the standard error. Usenet. How far are we? We've completed 1, 5, 7, and 9. We're so far away from being done. Oh man.
The trucking company wants to predict the yearly maintenance of the strips because. So under our data analysis toolpack, opening up our data analysis toolpack, opening up regression. We can't do a scatter plot here once we move into multiple regression. It doesn't work if we add in a third variable, an x-axis. If you look at it in 3 dimensions,
The X,
the real world, that would make sense.
X,
Add in an extra
X6.
variable, and you've got a 4th dimension, another variable, a 5th dimension. I don't know about you, but I live in a 3-dimensional world. It's a little bit difficult to imagine a 4-dimensional world, much less a 5-dimensional world or an n-dimensional world for those of you that like sci-fi stuff. So the bottom line is, as far as regressions and charts go, you can do a scatter plot for a simple linear regression, but for the multiple linear regression, we don't have that option. All right, so maintenance expense was given to us as our y variable. Our 2 x variables here are miles driven and age of truck, and you'll see that they need to be adjacent to each other so that they can be selected as a block. Right?
Oh wow.
Output here.
Ooh.
It's not asking us about any assumptions, so we'll just click OK.
Ooh. It's not that complicated because all you do is just select 2 of them at once. Wow. The y variable is the maintenance expense, and miles driven and age of the truck. Miles driven and age of the truck are the x variables, so we have to do data analysis. The y variable is the maintenance expense, hence the x range is going to be those 2 variables, and then the new worksheet will be this, and then okay, and auto fit. Now we probably have to do all the same things as before. Every single stinking thing is every stinking thing. And so, now let's go.
So the first thing was they wanted to know, was the model significant? And yes, the 7.6 times 10 to the negative 14 is a very small value.
There's P value is less than 0.05, so reject the null. Conclude that there is a significant linear relationship between the predictors, miles driven and age. The predictors, miles driven and age, and the maintenance expenses, and the maintenance maintenance expenses. Next time, I'm just gonna use text box. That was funny. That was funny. And
Again, what does this mean? This means maintenance expenses equals 0.2 for each mile maintenance increases.
okay, so the difference here is you say that plus that times that plus that times that. Oh my god. Equals 11.42 plus 0.07 times miles driven plus 10.71 times age of truck. Maintenance expense equals 1142 plus 0.07 times mile driven plus 10.71 times age of truck. For each additional mile driven, what? The maintenance expense increases by 0.07. Oh my gosh, for each additional year of age, the maintenance expense increases by blah. For each additional year of age, the maintenance expense increases by 10.71. So that's gotta be it, right? For each additional mile driven, the maintenance expense increases by this. For each additional year of age, the maintenance expense increases by 10.71. Derpy 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 derp derpy derp 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 derp.
What the question asks is, so the magnitude of age is 10.7. The magnitude of miles driven is very, very small at 0.07. Does it mean that miles driven isn't as important as age of truck? If you look at the p-value for each of these coefficients, this is something we're going to start doing in multiple regression. We see that the miles driven is a significant predictor. Its p-value is very small, 6.9 times 10 to the negative 8. Whereas age of truck has a p-value of 0.25, so it is not a significant predictor of maintenance expense. Even though it's so much larger in magnitude, the magnitude of the coefficient doesn't mean that it's more important or less important. Okay? Plus, when you think about it, it's going 7 cents for each mile. If you drive 1,000 miles, that's $70. Okay, so if you think about how many miles per year a truck is driven, probably a commercial truck, I don't know, 50,000, 100,000. So obviously miles driven is a significant predictor, but it also has more of an impact when you think about the quantity of miles driven in a year versus, a whole year, that's 12 months. You may accumulate a lot of miles. All right, so enough of that. Number 18.
So, I don't know. Really? That's all she did to answer the question? She skipped B, didn't she? She skipped B. Oh, man. She skipped B. Are you going to skip B? Don't skip B.
An antique collector becomes
Oh, no. She forgot about B. Interpret standard error of estimate in R squared. Dang it. Oh, no. I'm going to say the magnitude of the coefficients isn't as important as the p-values, which indicate that miles driven is a significant predictor of maintenance expense, but age of truck is not. We're going to say these. So, and anyways, well, I'll do is P, even though she didn't do it. Standard error. I'm going to just copy what I wrote for the first one. Because we didn't, that's the only time we did standard error. Stop taking forever. Stop taking forever. 98% of the data 68% of the data. What's the shortcut for? There's got to be a different one. I thought it was different. Control plus page up. You've got to be kidding me. I thought there was a different one. I thought there was a much better one. Really? Control page up and control page down? I thought there was a different one. There's got to be a different one. No. There's got to be a different one. I'm sure there was. Control tab is a better option. Here we go. So, control tab, 68% of the data falls within one standard, falls within one standard error of the regression line. And then the other one is Do I really need this one open? Maybe. R squared. R squared is goodness of fit. Goodness of fit dash. That was funny. Goodness of fit dash 95.12% of the variability in maintenance expense is explained by miles driven and age of truck. So there we go. That was funny. So I did standard error and R square. So I think that's good. Oh geez. So we're finished. Okay, so we are done with 5 out of 18. I'm going to calculate the percentage of the homework I've finished every time. We are done with 5 divided by 18. We are 27% done. Oh my gosh. Oh. That was funny, sniffs. Oh my gosh. Oh. You sniffed. Oh gosh. 18. An antique collector believes. That the price received for a particular item increases with its age and with the number of bidders. It contains data, multiple regression. Interpret each of the estimated coefficients. Equation, interpret the coefficients. Are they believing? Correct. Are they correct? Interpret standard error. And R squared, does it appear that the predictions of price from this equation will be very accurate? So, the price will depend on age and number of bidders, and it's going to be the same exact type of problem as before. Exactly the same. There's no difference except for the types of data that we're using.
Filed for the auction to account for each of the sibling.
Derpity derp 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 derp.
Same spot. Then go ahead and click OK.
Derp 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 derp. Data analysis. This one is going to be the auction price, and this one is going to be these two things, and there. So we obtained 94.89. Oh, come on. Where's it going? Oh. And we got the significance of 8.7 876. Oh no! How did we get different? Oh, it's probably because. Oh, never mind. Wait. So 876 e to the negative 15, and we got like 1,336 for the intercept, and there's 12.7 and 85.8. So it looks like we got all the correct numbers, and it's going to be all the same stuff as before. So
It's very small.
p-value is small, so reject the null. So p-value is less than 0.05, so reject the null. Conclude that there is a significant. I think, you know what? I'm gonna just make it a text box here because I keep having the problem of stuff. So conclude that there is a significant linear relationship between the oh my gosh. Conclude that. Wait, why are we using 0.01? Why are we using 0.01? It should be 0.05.
And I'm going to just cut it short here, go on to, and I'm going to just cut it short here, go on to explaining the model. So we're saying that the price.
Ha 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 ha. I don't care. She can take some points off if she wants to. I don't really care. It's gonna barely affect my grade anyways. If she does, which I highly doubt she's going to do. So, next, stop. You can now stop and look at this. We have price equals that plus negative number. I wonder if that's something. We have something or other and a something or other. And a blah 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 blah. Oh no, I clicked on the wrong thing. Price equals -1337 plus 12.74 times age of item plus 85.82 times number of bidders. So that plus this plus that times that and for each additional year of age, the price increases always increases. The price increases by 12.74 for each additional year of each additional number of bidders. The price increases by 85.82.
By $85.
And then
Yes, the antique collector is right in that both these things increase the selling price. However, if I was the antique collector and I was gonna spend time either finding items that were older or increasing the number of people at my auction, I would invest my time in increasing the number of people at my auction. Because for each additional bidder, you're getting 85, almost 86 more dollars versus each additional year of age, you're only getting 12.73. So far more important to have lots of bidders if you want to get good prices in your items. Restaurant in Bloomington, Indiana.
Uh-oh.
For the past 19 years, he's also recorded data on potentially relevant.
No freaking way. Are you kidding me? She skipped B again. She skipped B. Is she going to mention why she skipped B? The heck?
Far more important to have lots of bidders if you want.
She skipped it again. No. Why is she skipping it? I don't get it. Like, is there a reason for this? She just doesn't mention why she skips B. Well, maybe I should just skip them at this point, because, like, she skips them. I don't know. I'm going to do them anyway, because what if she takes points off because I skipped those parts? R squared. Uh, 68% of data falls in one standard error of the regression line, and R squared 89.27% of price can be explained by age of item and number of bidders. Wait, is that what it is? Oh, yeah. Variability in this is explained by it. Variability. Variability in price can be explained by age of item and number of bidders. And 68% of data falls within one standard error of the regression line. And price is like anywhere from like $700 to $2,000, so could be off by about $100. Like most of the time, it's only gonna be off by $100 to $200, but it will still get the general price. It appears that the predictions. Wait, hold on. It appears that the predictions of price from this equation will be accurate. I don't know why she's skipping B. I don't know why. We are done with 6 out of 18. That means 1/3. We have finally finished 1/3 of what we need to do today. Oh my goodness. Oh my goodness. 1/3. We are 1/3 of the way done of. Oh my gosh. How close are we to the end of this one? We only have 3 more in this particular assignment. 23. $23. 10, 23. Advertising. Oh. Simple linear regression for annual sales and the population residing within the 10 miles of the restaurant. Then interpret R squared. And then we have a bunch of more stuff. That's fine. We have completed 1/3 of today's problems so far. After an hour and 46 minutes. Oh, man. Number 23. 23. So we are going to do a simple linear regression equation with annual sales and the size of the population residing within 10 miles of the restaurant. Size of population within 10 miles of the restaurant. So that's going to be pretty that's funny, simple for that particular part.
The restaurant.
So,
I'll do that tomorrow morning.
What?
Another session.
Whoa, what are you doing? What are you doing?
I think we're gonna have to schedule another session to go over 26 and 27. I'll do that tomorrow morning.
Oh no! Oh no! 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 Oh no! 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 That means that she didn't cover those problems in the videos that she provided. You've got to be kidding me! No! Please! Oh no! I hope it's just all the same stuff as before. Oh That was funny.
Bring up the regression.
Sales and population, because we're just doing one for A. We're just doing population. So
It's terrible, but it is not a significant no.
okay. Stop. This one is going to be population, and we're going to do A. And there. So we have auto fit column width, and we got a 0.55, we got a 0.14, a 0.02. Not good. So what's the question again? Let's see. R squared. It says interpret R squared. I mean, R squared, that's very small. But she's probably going to do the whole stinking thing. P, fail to reject the null. P, value is less than, more than 0.05, so reject the null. Did she say 0.01 again? No.
Population. So then it, now annual advertising expenditure.
What about R squared? What about R squared? Like, she just completely ignored R squared again. Like, what the heck?
So then it says in part B.
I'm just going to ignore it. Because she ignored it, I'm going to ignore it.
Add then another explanatory variable, annual advertising expenditure.
So, add another one to the regression equation, part A. So we're going to have both of them included, both the population and the what was it again? Oh, come on. Annual advertising expenditures. We're going to have
our X input range is going to be the population and the advertising expenditure. So go ahead and click OK.
So this is going to be for B, and so we're going to do this. A is this. Oh, stop being dumb, dang it. I wish you could just, okay. This is going to be population and advertising expense. And this is going to be B. And now we have auto fit, and we have now reached a P significance of 0.068, still above 0.05, and we have R square of 0.29. That stuff. So, and the p-value for advertising is actually 0.03. So, looks like maybe advertising is significant, but not the other one.
Now we see that we're getting better at 0.067, so it's still not significant, but it is close.
P-value is more than 0.05, so fail to reject the null. Wait, what did I say earlier? No. I wrote this wrong. Fail to reject the null. That's what I meant to write this. Fail to reject the null. B. We have A, B. So that's funny.
Now it's asking us to run this a third time.
Really? Like, are we just gonna skip all the other stuff in the question? I don't even know what the adjusted R squared means. But she's just skipping over all this crap. Previous year's advertising expenditure. So let's see if this helps. Stop. So we will also include previous year advertising expenditures. So, okay, hopefully we get the same thing here. Oh. This one will be these three go down. New worksheet is going to be on C, and we have the thingy, and now we have a very low p-value. Oh my gosh. 2.31 to the negative 14th p-value. Insert text box. P-value is less than 0.05, so reject the null. Conclude that, watch as she shortens it to there's a significant linear relationship again. Sales and predictor variables. There is a significant linear relationship between sales and the predictor variables, and I don't feel like writing anything else for the model. Now what?
So one of the things they want us to look at is the trend here through these three that we ran in terms of the increases in our correlation coefficient and our fitness fit. So we see that it's
really? Wait. Where? Dude, they keep saying R squared and adjusted R squared. They never ask us to look at the multiple R. Like, what on earth? What is adjusted R squared anyways? Alright, well, I'm just going to do it the way she says to do it. So.
2% of the variability is explained by the model. We added our second variable in, and we see that multiple R, or the Pearson correlation coefficient, is up to 50, so it's in the middle of the moderate range, and we now have about 28.6% of the variability explained by the model. So it's getting better each of these times. Now, in our final model with the additional predictor variable in there, we see that our Pearson correlation coefficient is moved up to a whopping 99. So this is
oh my gosh.
0.90. So it is a very strong relationship.
Greater than 0.90. Greater than 0.9, so very strong relationship. Dude, it's almost 1-to-1 at this point. Wow. How does that happen? How is that even possible? It looks like the previous advertising is actually having a giant effect. Wait a minute. Yeah. Wait a minute. How on earth are these p-values getting to be so good every time? What the heck? I thought they would be the same every time. Right. Like the population one should, I thought it would always be certain amount. No, the population keeps on having a p-value that keeps decreasing. Population is 0.55 here. Here it's 0.50, and then here it's all the way down to 2 times 10 to the negative 6. The heck? Weird.
And it looks like 98.99, so about approximately 99% variability.
99% of variability in sales is explained by
Sale.
By the model. How did I end up with that?
Anytime you add these values increase, well, first off, anytime you add additional predictor variables, your Pearson correlation automatically increases. It will, every time you add a predictor variable, your Pearson gets bigger. Okay. One of the things to keep in mind then is that since R and R squared are related to each other, right? R and R squared. Okay. So if the Pearson correlation coefficient gets larger, so does the R squared. Is that increase in R squared actually an improvement in the fit, or is it just an artifact of adding additional predictive variables? In this case, you can determine that by looking at what we call adjusted R squared. Basically, if you add 5 or more predictor variables, you want to automatically choose the adjusted R squared because that's going to take into account the number of additional variables and reduce that R squared to a more realistic range. And I don't want to try to explain all the math behind that. Just trust me that that's what that does. Okay. So looking here at 0.98699 versus 9843, that's a pretty minimal difference. So again, I would say that in this situation, there's not a lot of inflation of my Pearson correlation coefficient going on by adding the additional variables. Those additional variables are actually accounting for that much additional fit, or that they're adding to the strength of the relationship. It's not an artifact of how many variables you have. All right. So we'll talk more about this adjusted R squared as we finish this chapter and we get to chapter 11. Part of the reason I don't have enough time here to finish is that these last 2 problems we're going to have to do some dummy variables.
Oh no, dude.
They're not stupid. But I need to explain why you use them and how they
Dude.
So having said that, I hope you guys all have a fantastic Saturday. I know if you're anywhere near me, it looks beautiful out other than the wind. So
I'll write something for our adjusted. Adjusted R squared. So wow. Adjusted R squared. Wow. So we have R squared. So adjusted r squared, and adjusted r squared. So first we have r squared of low r squared, low percentage. I'm just gonna say low percentage. Not model does not predict sales variability in sales well, or something like that. B r squared and adjusted r squared. Now r squared is higher than before, so slightly. So model is better predictor of sale variability in sales, and adjusted r square is about 9% less than is a bit less, a decent amount less than r square. Adjusted r square gives a more realistic indication of the goodness of the, I guess. And then now adjusted r square is very close to r square. These results are much stronger, indicate much better fit, indicate goodness of fit, that this model is a much better predictor of variability in sales. Okay. Oh, just rushing through all those. And now hopefully I somehow doubt that there's going to be a video on the last two problems. No. Where's my ruler? Where is it? We're done. No, there's not going to be a video for the last two problems.